So section 7 is about interacting objects. So we're going to be using Newton's second law and third laws to be applying those to interacting objects. So a reminder of Newton's third law is here. Every force is occurring as one member of an action and reaction pair of forces. The two members of the pair will always act on different objects. And then the two members of the action-reaction pair will always point in opposite directions and are equal in magnitude. So that is what the cutesy phrase is referring to. We know what I mean by the cutesy phrase, right? Okay.
I won't say it. I don't want to give you.
What is Newton's second law? Okay. Or F equals ma. That's what we've been using so far in this chapter, for the most part. Okay, so we are using these two laws now in this section together. So when two objects are in contact and their motion is linked, we need to duplicate a couple of things in our analysis. So we'll draw each object separately and prepare separate force identification. That's diagrams for each object. Separate free body diagram for each object. So that's each object. Very important. And then write Newton's second law in component form for each object. So that means some of the forces in the x direction, some of the forces in the y direction, and we'll do that for each object. So we have a separate free body diagram, separate sum of the forces for each object. And then we'll write Newton's second law in component form for each object. So that's going to give us several equations to deal with. And then we're going to use those equations kind of combined. We'll have several variables, and possibly we're going to be using substitution to get those equations solved for the thing that we're looking for. So in number 4 now, identify the action-reaction pair of forces. Remember, action-reaction pair means one is going in one direction, the other one's going in the other direction, but they are in equal magnitude, okay? So if object A acts on object B, notice the notation here. Object A is acting on object B. Then identify the force object B acting on object A in the opposite direction. Okay? So we have FB on A, we have FA on B. Newton's third law says you can equate these two forces. So FA on B equals FB on A. Objects in contact will also have the same acceleration if they're moving. So if they're not moving, I guess they also have the same acceleration as well. They're just zero, right? But if they're in contact, then they're going to have the same acceleration in the same direction. And they have the same F net then as well. Okay, so those are important ideas. And we're going to go straight into our example for this section. We have a 5 kilogram block A being pushed by a 3.0 Newton force. In front of this block is a 10 kilogram, that's a 10.0 kilogram block B. So we'll put a kilogram there. Probably 1 o'clock in the morning when I type that one up. The two blocks move together. That's important information. So they're moving together, which means we're going to be using Newton's third law here. What force does block A exert on block B? So the surface's frictionless also is important. So the first thing we're going to do here is draw like the pictorial overview. Okay, we want to draw the picture of what's happening. So we will draw the picture. We have pushing on the ground, so I'm drawing the ground. And then we have some block. So the 5 kilogram block A is being pushed by a 3 Newton force. So I'm going to draw my block. Thank you. I'm kind of cheating. It's being pushed by a 3 Newton force. So what's pushing it? Something. Maybe it's my hand. So I have this hand.
Wow.
I know, it's great. Okay, now in front of my block is another block. It's 10 kilograms. So how am I going to draw this block?
Bigger block.
A bigger block. There it is. It's awesome. Okay. Oh, sure. What should we label them? A and B. Okay, so this is block A, this is block B. So as I'm pushing these blocks, they're moving together. All right? So there's our picture. Now, how am I pushing this block? Well, I'm pushing it this way, obviously, with a 3 Newton force. All right, so my picture's done. Now I'm going to go into free body diagrams. So on my first block, so this is the free body diagram for block A. And then over here, I'll draw my free body diagram for block B.
Sorry.
So on block A, I have a weight down.
And normal force up.
So that would be the weight of block A. I have a normal force up. Those should be the same. Normal force of block A.
3 Newton force going to the right.
I have what?
3 Newton force going to the right.
Okay, so I'm going to call that something.
Force.
So force of the what?
Push.
It's the force of the hand. Since we drew a hand, we might as well call it the hand. So that's my force of the hand. Now,
You're going to have friction, won't you?
I don't have any friction,
Frictionless.
but I do have something pushing back on me. What is it?
Newton's
Block A.
I have the force of B, block B, on block A. Okay? That completes my free body diagram. The reason I have force of B on A is because I have an action-reaction pair going on with A and B. Block A is pushing on block B, and block B is pushing on block A. So I have an action-reaction pair there. So it's B on A with our free body diagram for block A. Now, for block B.
Wait, don't we need it for F net?
Oh, we have an F net.
0?
Is it 0?
No.
Well, no, it'd be going to the right.
It'd be going to the right. So we need to draw an F net. And that is to the right.
good job reminding me.
Thank you. All right. Block B, what do we have?
Weight, normal force.
Okay, weight down. W sub B. Normal force up. N sub B. Okay, now what?
You got force to the right, which is
To the right is a force A on B.
and to the left would be B on A, wouldn't it?
No,
No, there's no other force acting on it.
that's it. We don't have the force of the hand here because the hand is not touching block B. We just have the force of block A on B. We don't have force B on A here because B is pushing on A, not the other way around. So that force is only on block A. So we have just A on B, and that's it.
Well, then you got that net.
We have an F net here. Which way is it going? Okay. All right, so those are our free body diagrams. Now we're going to do some of the forces. Now, if I did some of the forces in the y direction for block A, what would I see? They're going to be equal. Okay, so I'd have normal force A up, so then minus weight down equals 0. We're not accelerating in the y direction. And that would be the same for B. And I'm just going to have the weight equals the normal force. Nothing's happening here, okay? So I'm going to skip the y direction. I'm going to go straight to some of the forces in the x direction. So some of the forces in the x direction, actually I'm going to change colors.
So are you going to do some of the forces in the x direction for A and some of the forces in the
Yes, we have to do it for both.
So F. or
Some of the forces
X direction A.
in the x direction equals, what do I have for A?
Um,
So yeah, I have the force of the hand. and then minus FB on A.
Can we just call it llama? I think that sounds so much better.
No.
Great. Great.
Is that it?
Equals
Equals what?
0.
Okay, yeah, we do not have a balance of forces here, so we're going to say equals MA, except this is M, the mass of block A, right? So it's MA. And then also the acceleration of A.
Ah.
Okay, now the sum of the forces in the x direction for the other one. So we have sum of the forces in the x direction here equals what? Just FA on B. It is going in the positive direction. So it's positive FA on B. And that's it. Equals
M sub B.
M sub B. Acceleration for block B. Okay, now earlier we talked about the fact that if the blocks are being pushed together, if the objects are being pushed together, then objects in contact will have the same acceleration. I said that right here. Objects in contact have the same acceleration. So
AB.
AA and AB are actually the same thing, okay? Those are actually going to be called, we can call them A sub X. So let's go ahead and change those right now. Let's change A sub A and A sub B, and let's just call those A sub X. Acceleration in the X direction. Okay, so now what we can do is, it says, what force does block A exert on block B? So what are we looking for? Yeah, we're looking for FA on B. We're looking for this guy right here. All right? Do I know the mass of B?
Yes.
Do I know A sub X? No. Okay, but this A sub X in the right-hand equation is the same as the A sub X in the left-hand equation. So if I solve for the A sub X in the left-hand equation, I can substitute it into the right-hand equation. Agreed? Okay. Do I know M sub A?
Yeah. Yes.
Okay. Do I know FB on A?
No.
No. Do I know F sub H?
No.
Yes.
Yes, I do. It's the force of the hand, right? That was 3 newtons. Okay. So that's pretty good. So there's actually 3 things here that I don't know. I don't know the acceleration. I don't know FB on A. And I don't know FA on B, right?
Right.
Okay. But I do know something. I know that this guy and this guy are equal because those are equal and opposite cutesy phrase, right? Newton's third law. Those are action-reaction pairs, and when we have an action-reaction pair, they are equal in magnitude, opposite in direction. Agree with that? Okay. So FB on A and FA on B are actually the same magnitude, just acting in opposite directions. That's going to be important for us. So what we need to do here is solve one equation for one of these unknown things, substitute it into the other equation, and we're going to be in pretty decent shape.
Let's solve.
So the issue here is we want FA on B equals in the end, right? Because we're looking for what force does block A exert on block B. So that's FA on B. Hopefully you agree with that. Now, the things that are variables here are, that we don't know, are A sub X, FA on B, and FB on A. Okay? But we know FB on A and FA on B are action-reaction pairs. So those are essentially the same thing. So we can pretend for a second that FB on A and FA on B are the same. So really we only have 2 things here that we don't know. Acceleration and FA on B. Okay? Because I'm looking for FA on B, I don't want to solve right now for FA on B, because when I use substitution, that will get rid of FA on B. Instead, I want to solve for A, acceleration, because now when I substitute acceleration into the other equation, that will get rid of acceleration and leave me with FA on B, the thing I don't know, which is the thing that I'm looking for. So I'm going to solve one of these equations for acceleration so that I can substitute it into the other equation and leave me with the thing that I'm looking for, okay? So the easiest one to solve for acceleration is the one on the right. So I'm going to divide both sides here by the mass of B, which gives me acceleration in the x direction equals FA on B over mass of B. All right, now I'm going to take this acceleration that I just found and plug it into the other equation. So now I have F sub H minus FB on A equals mass of A, and then times what I just got for acceleration, which is FA on B divided by the mass of B. Okay, so now the goal is to find the force of block A on B. Okay, so I need to solve for that guy right there. So the next thing I gotta do is remember that FA on B is the same basically as FB on A. Okay? Let's start working on this problem though, getting FA on B by itself. So let's first maybe move F that's negative FB on A to the other side. So we have F sub H equals, and then I'm going to rewrite this MA times FA on B divided by MB. I'm going to write this as MA over MB times, off to the side, FA on B. Hopefully you see that that's a totally legal thing to do. And then I added FB on A to both sides, so plus FB on A.
Oh, what is it supposed to, or, no, wait, if you subtract it, never mind.
Now, FA on B and FB on A are the same force, right? So I can call FB on A the same thing as FA on B.
So it would just be 2.
So I'm going to switch this here to FA on B.
So we have 2 FA on B?
We don't have 2 FA on B. We just have FA on B sitting there, and we have FA on B sitting somewhere else right now. But what I can do is I can factor out a GCF. So now I have F sub H equals, now factor out a GCF of FA on B. Open up parentheses and what's left over. We have, yes, MA over MB plus 1. And now I can divide by this leftover thing after I pulled out the GCF, and that will leave me with FA on B all by itself. So I'll have FA on B equals the force of the hand divided by the mass of A divided by the mass of B plus 1, all in the denominator. And the nice thing is,
Those are all numbers.
I did all of that without knowing what the force of the hand was, or the mass of A, or the mass of B. And now I can go back up and look and find out what those things are. So the force of the hand was 3 newtons divided by the mass of A, which was 5 kilograms. The mass of B was 10 kilograms. And then plus 1, all in the denominator. So now 5 divided by 10 is 1/2. 1/2 plus 1 is 3/2. So I have 3 newtons divided by a unitless 3/2. Leave it, change it, flip it in the denominator, and we have 3 times 2/3. The 3 and the denominator is gone, and I'm left with 2. Actually, 2.0 newtons if I carry through with the significant figures. And I didn't even need to use a calculator. So that's how you do that problem.
Simple.
Yeah, so keep working with the forces, the free body diagrams, and not the numbers. And you'll see how this math boils down. Sometimes things will divide out, and you won't even need some of these letters that you're working with as you go. Okay, one more thing here, and we're actually done learning about the section. We have boxes P and Q are sliding to the right across a frictionless table. The hand H is slowing them down. The mass of P is larger than the mass of Q. Rank in order from largest to smallest the horizontal forces on P, Q, and H. Take a minute to think about it. Help yourself by drawing force diagrams and whatever else you need to do to come up with the correct answer.
Yeah,
So you're eliminating D immediately because what?
because the forces are not equal. The forces that should be equal.
Which forces should be equal?
FP on Q and Q on P.
So P on Q and Q on P, we should have an action-reaction pair there.
Yeah.
So we should have that, and we don't have that in D. Okay, good.
And I don't think it's A.
Based on the previous problem,
They're not-
yeah,
they're
they
not
can't.
all equal.
They can't all be equal?
Yeah.
No. Because they don't have the same mass.
They don't have the same mass. Okay, good. So we can eliminate A.
Yeah.
All
I
right.
think it's C. Well, based on the previous problem, so we have.
Mine's
Sorry,
got it.
So we have, based on the previous problem, right? The hand is exerting a force, right? But since these things, since it's being the force or the energy, since these things are already set in motion, right? The hand is slowing them down, like this, kind of.
The hand is slowing them down, yep.
And so I figure that P, the box P must be acting on the hand greater,
Would be less than. It's slowing down.
What is the key to this problem?
It's being slowed down.
It is being slowed down. What does that mean?
That means that the hand is slowing down P, E, and Q.
Yes, but what does that mean?
that
That
the
means
objects
the
were
hand
already
has
in
to be
motion.
greater.
Well, yeah, they were already in motion, but what does that mean?
It has to be a greater force
Yeah.
to stop them from moving.
Well, B.
So you're talking about if the velocity is going to the right and they're slowing down, then the
Acceleration is going to the
acceleration is that way, which means the
Hand must be exerting greater force.
you're not thinking about forces. If the acceleration is to the left, then what else is to the left?
Net force.
F net is also to the left. Okay, now we can think about the rest of the answer. F net is to the left. So FQ on H and FH on Q. Is that going to be greater than or less than FP on Q and FQ on P? It'll be greater than. The answer is B.
Boo! Do it.
You got to think about the F net. You got to think about the acceleration.
Yeah.
That will dictate.